This is Unit 4, Part D, and we are looking, or Part E rather, and we're looking at some examples of U substitutions. So we'd said that when we wanted to pick a U value for the U substitution, we always want to look for the inner function of a composition. When you look at example 1 here, remember that that sixth power on the cosine could actually be rewritten so that it looks like cosine x to the sixth power times sine x dx. Now that I've written it in that form, it's probably more obvious that this cosine x is inside that exponential function, that sixth power. And so cosine x would make a good choice for u. So let's do that. Let's let u be cosine x. I'll take my derivative. So du dx is negative sine x. And du would be negative sine x dx. I'd like to keep the x's all together, but that negative sign, I could actually divide that out, bring it over to the other side, so I'll go ahead and do that. That should be everything I need for the U substitution. All right, so I'm going to replace this cosine x with a u. So first of all, I will have the integral of u to the sixth power. And then this sine x dx, I can replace that with a negative du. All right, that multiplier of -1, basically, I can pull that out in front. And then the antiderivative power rule here would be u to the 7th divided by 7, plus my constant of integration. So I end up with -1/7, u, which is cosine of x, to the 7th power, or cosine to the 7th power of x, plus c. Take a look at example 2. I have e to the 4x, secant squared, e to the 4x. That e to the 4x is definitely the inner function for secant squared. So that's going to be a good choice for my u. That means that du dx would be e to the 4x times 4. There's a chain rule there. So du is 4e to the 4x times dx. And again, I want to keep the x's together, but I can divide out the 4. So 1/4 du equals e to the 4x dx. Coming back to my integral, I need to be a little bit careful here. I have that e to the 4x in 2 places, but it's only an inner function here. So I'm going to go ahead and replace just this e to the 4x with u. So I'll have secant squared of u. Now I still have this other e to the 4x and the dx out here, and together I can make this replacement for the 1/4 du. So times 1/4 du. All right, the 1/4 can be brought out in front of the integral. And then fortunately, I think secant squared u I can do, right? It's on my list here. The integral of secant squared x dx is tangent x. So for secant squared u du, I would have tangent u. And the only thing left to do is plug back in for the u. That would be 1/4 times the tangent of e to the 4x plus c. By the way, on any of these, I would encourage you to check them by doing the derivative and verifying that you get back what you started with. All right, what about number 3? Secant squared x, tangent squared x, dx. Let's start with what's tempting but wrong. Secant x tangent x dx has an integral that's secant x. It's not true that if I square this, I square that. There is no rule that says that, right? I can deal with sums, differences, and constant multiples, nothing else. So even though I know it's tempting, this isn't going to help me out, or at least not in this part of the problem. Instead, I'm going to look toward a U substitution. First of all, let me think of this as secant of x squared times tangent of x squared dx. There are actually 2 candidates for the inner function here. I could let u be secant x, or I could let u be tangent of x. Which one's going to work better? Well, to answer that question, think about the derivatives, right? As soon as I pick one of them to be u, I'm going to have to take the derivative, du dx. What's the derivative of secant x? Secant x tangent x. Maybe not so helpful. What's the derivative of tangent x? Secant squared x. That's sitting right there. So I think the tangent x is going to be the better choice here for u. So we'll let u be this inner function, tangent x. That way du dx is secant squared x, and du is secant squared x dx. That's perfect since I happen to have that sitting right there. So I'm going to replace the tangent x with the u. So I'll actually have u squared. And then I'm going to replace secant squared x dx with just a plain old du this time. And notice I got a really nice simple integral out of that. Amazing. That's going to integrate to u cubed over 3 with my power rule, or 1/3. And since u is tangent x, that would be tangent cubed x plus c. All right, looks good. I'll try one more example of these slightly more complicated U substitutions. In example 4, I have the integral of x minus 2 e to the x squared minus 4x. Although the x minus 2 is in parentheses, it's not really inside any other function, so it's probably not going to be my best choice for you. Instead, I'm looking at this x squared minus 4x. That's inside the exponential function, making it a good candidate for u. So let's do that. U is x squared minus 4x. That would mean du dx is 2x minus 4. And du is 2x minus 4 dx. As I look at this, I can see this is just going to become e to the u. That's no problem. But I don't quite have 2x minus 4 dx. Instead, I have x minus 2 dx. Well, being good algebra students, I'm sure you've already recognized that if I factored out the 2, I would get the x minus 2 that I need. So let's go back and do that. I'll keep all the x pieces on this side, but I can divide out the 2. And there we go. That was exactly what I needed. I can now take this x minus 2 dx and replace it exactly with a 1/2 du. All right, that's looking pretty good. 1/2 could just come out in front, and then the integral of e to the u is still e to the u. So I end up with 1/2 e to the x squared minus 4x plus c. All right, the next couple of examples, we have something a little bit different happening. We're still going to go with a U substitution, but there's going to be one extra step to make these next couple of problems work out. As you look at this first example in section C, I would assume that you would look at that 2x plus 5 and say, since that's inside the square root, it would make a good choice for u, and I would certainly agree. Let's let u be 2x plus 5. du dx is just 2, so du is equal to 2 dx. And I can divide out the 2, so 1/2 du is equal to dx. All right, over here in my integral, I definitely can replace that 2x plus 5 with the u. So I'd have the square root of u. But now I'm going to run into trouble. I can replace just the dx with 1/2 du. That's not a problem. But what is a problem is there's something in my integral that I haven't accounted for. What about that x? I didn't use that anywhere down here. And I have to account for everything. So here's the extra step that I was talking about. When that happens, what I'm going to do is I'm going to go back to my original definition of u. And I'm actually going to solve that equation for x. So I would have u minus 5 equals 2x. U minus 5 over 2 equals x. And I'm going to replace that x with u minus 5 over 2. All right, made it a little more complicated, but I think we can still handle this. Looks like I'm going to have a 4 in the denominator, so let me start by factoring that out. I'll put a 1/4 out in front. That's really u to the 1/2. I've got that multiplier of u minus 5, and then I've got my du. So it looks a little bit neater when I kind of collect everything there. This is a product, but it's a product I can do. I can multiply that out. So it would become u to the 3/2 minus 5u to the 1/2. All right, that's starting to look pretty good. Those are just power rules. So let's see, adding 1 to the exponent would give me u to the 5/2. And if you guys are about ready for a little shortcut here, when we divide by 5/2, that's the same as multiplying by the reciprocal, 2/5. So I'm just going to write it that way right now. Subtract 5 times, power rule here, add 1 to the exponent, and I get 3/2. Dividing by 3/2 would be the same as multiplying by 2/3. All right, so let's see what we've got here. This would become 2/20ths. Excuse me, u to the 5/2. Minus this would become 10/12ths. U to the 3/2. Or in lowest terms, 1/10. And remember, u is actually 2x minus 5 to the 5/2 power. Subtract 5/6 times 2x. Oops, I'm sorry, that was a plus 5. Plus 5 to the 3/2 power plus c. All right. It's not the most elegant answer. Kind of a big, long thing. And that's pretty typical when you have these ones with the extra step like this. But it is the correct antiderivative. All right, let's do one more problem of that type. As I look at example 2, the first thing I notice is that I've got an x plus 1 under the square root. That's an inner function. So let's start with that. I'm going to let u be x plus 1. du dx would just be 1. So du is equal to dx this time. That part seems pretty simple. So let's start making the substitution. Under my radical, this x plus 1 is just going to turn into a u. So in the denominator, I've got the square root of u. And then the dx itself can get replaced with a du. The problem that I have is the x squared. I haven't had anything to do with that yet. It hasn't gone anywhere. I can't just put it down here because I can't mix x's and u's. So I need to figure out something to do with that x squared. Just like last time, we're going to come back over here and say, well, what if we solve this for x? X would be u minus 1. And so I'm going to replace the x squared with u minus 1 squared. I now have an integral entirely in terms of u's, which is exactly what I need. So let's start working on that. It's not in a form I can integrate yet, but I should be able to get there. I'm going to use that trick that we've used a few times before. I'm going to take that square root of u, it's in the denominator, so I'm going to bring that up as a u to the negative 1/2. And then I'm going to square this out. U squared minus 2u plus 1. I can distribute the u to the negative 1/2, which would give me u to the 3/2 minus 2u to the 1/2 plus u to the negative 1/2. And I've now got 3 terms, each of which is just a power rule. So I'll get u to the 5/2. Dividing by 5/2 is the same as multiplying by 2/5. Minus 2 times. Increase that power by 1 gives me u to the 3/2. And again, dividing by 3/2 is the same as multiplying by 2/3. Plus, adding 1 to that exponent gives me u to the positive 1/2. Dividing by 1/2 is the same as multiplying by 2. And don't forget my constant of integration there. All right, we basically have it. I'm going to simplify just a little bit, mostly just multiply those numbers. And as I do that, I'm going to put back in the u is actually x plus 1. So I have 2/5 times x plus 1 to the 5/2 minus 4/3 times x plus 1 to the 3/2 plus 2 times x plus 1 to the 1/2 plus c. And again, really typical of these problems, they often have some kind of long, drawn-out answers. But we got there. All right. The last couple of examples are going to combine this idea of U substitutions with definite integrals. The main thing to remember here is that in a definite integral, the values, the -2 and the 4 here, are always values of the original variable, x. So I have to make sure that when I plug them in, I don't do it too early. I have to wait till I get the x's back before I can substitute in the -2 and the 4. So let's go ahead with this. As I'm looking at this and thinking about my U substitutions, it looks to me like the inner function here would be x squared plus 8. So let's make that our U, meaning that du dx would be 2x, and du is 2x times dx, so 1/2 du is equal to x dx. Coming over here to do my integral, I'm going to replace the x squared plus 8 with a u. So that will actually be u to the 4th power. And then the x dx, which I have right here, gets replaced with a 1/2 du. Everything's accounted for. There's no leftover pieces, so I don't have any extra steps this time. This is looking pretty good. Now I'm going to call your attention to the fact that I didn't put the -2 and the 4 as the limits of integration, because again, those are x values. This is a u integral. Those aren't values of u, so I'm not going to write them in right now. Instead, I'm going to do this antiderivative. 1/2 times u to the 5th over 5. I won't bother with the plus c since I'm eventually going to do my fundamental theorem of calculus. So I have 1/10 times the u, which is actually x squared plus 8 to the 5th power. And now that I've got the x back, I'll put my limits of integration in to do that FTC. Okay. So I don't put the -2 and the 4 in when they're u's. I only put them back in once I get back to the x's. All right, we're going to have some pretty big numbers here, but we'll manage. We'll have 1/10 times, I plug the 4 in first, so 4 squared plus 8 to the 5th power, 24 to the 5th power, that's going to be a pretty big number, minus 1/10 times, and now I'll plug in the -2. -2 squared plus 8 to the 5th power, and that's just going to be a calculator problem. Let's see what we have here. We have 1/10, which is 0.1. 16 and 8 is 24 to that 5th power. Minus, again, 1/10 is 0.1. Times, that would be 4 plus 8, which would be 12 to the 5th power. And there's that big number that I was kind of expecting as an answer, a really large number. 771,379.2. All right. We're getting a little long, but we've only got one problem left, so let's go ahead and finish it up. One more fundamental theorem of calculus problem. I've got a definite integral here again. And as I'm looking at this integrand, I see that sine 2x plus 3 that's inside the radical. That's my inner function. That's my u. All right, du dx would be the derivative of sine 2x is cosine 2x. Don't forget your chain rule here. derivative of that 2x would be times 2. So du is 2 cosine 2x dx. I can divide out the 2 that's the coefficient, so 1/2 du is equal to cosine 2x dx. That's all looking pretty good. So let's make the U substitution. Since I'm going to go to U's, I won't write my limits of integration. Those are x values. And everything that's under this radical gets replaced by the U. So I have the square root of U. And then the cosine 2x dx is exactly what I needed to replace with 1/2 du. So that integral definitely got a whole lot simpler with my U substitution. That's what we like to see happening, right? I'm going to pull the 1/2 out and just rewrite that as u to the 1/2 du to make it a little bit easier to see my power rule here. Increasing the exponent by 1 gives me u to the 3/2, and dividing by 3/2 is the same as multiplying by 2/3. Again, I won't bother with the plus c because it's a definite integral. So I get 1/3, and my u is sine 2x plus 3 to the 3/2 power. Now that I've got the x's back in, I can plug in my limits of integration from 0 to pi halves. All right, fundamental theorem. Plug the pi halves in first. So I'd have 1/3 sine of 2 times pi halves would just be pi plus 3 to the 3/2 power. Subtract 1/3 sine of 0 plus 3 to the 3/2 power. Sine of pi is 0, so that's just 3 to the 3/2 power. And sine of 0 is also 0, so this is also 3 to the 3/2 power. So I've just got something minus itself, and the value of this integral is 0. All right, that brings us to the end of topic E.